Welcome to Astronomy Daily, your source for the latest space and astronomy news. I'm your host, Anna, and today we'll be diving into some fascinating stories from across the cosmos. We have quite a lineup of cosmic discoveries and developments to explore. We'll begin with an intriguing roadmap for potential sample return missions from our solar system's most inhospitable planets, Mercury and Venus. These ambitious missions could help fill critical gaps in our understanding of the inner solar system. Then, we'll examine a surprising new theory about the origins of Earth's water that challenges conventional wisdom about asteroid impacts, delivering our planet's life-giving resource. We'll also explore the dawn of a new space age that some are comparing to the revolutionary age of sail in the 1600s, with all its opportunities and challenges for humanity's expansion beyond Earth. The James Webb Space Telescope continues to amaze us with its observations, and we'll look at its latest examination of a complex nebula with a fascinating history that dates back to William Herschel's observations in 1790. Finally, we'll provide a helpful guide to spotting two upcoming meteor showers, the Lyrids and Eta Aquarids, that will grace our night skies beginning in late April. So buckle up for a journey through the latest astronomical discoveries that are expanding our understanding of the universe. For our first story today, ponder this. How can we successfully collect and return samples from the two innermost planets of our solar system, Mercury and Venus? This fascinating question was recently tackled by researchers at the California Institute of Technology in a study presented at the 56th Lunar and Planetary Science Conference. The team outlined potential roadmaps for what would be groundbreaking missions to these challenging destinations. These aren't just academic exercises. Sample return missions from Mercury and Venus could help scientists fill a significant knowledge gap in our understanding of the solar system's formation. What makes this particularly interesting is that despite the thousands of meteorites in our collections, we don't have a single confirmed meteorite that originated from either Mercury or Venus. When you think about it, this is quite remarkable. We have meteorites from Mars, from asteroids, and even from the Kuiper Belt beyond Neptune, but nothing from our closest planetary neighbors. This absence creates a substantial blind spot in our understanding of the planetary building materials of the inner solar system. Tengi Tony Yap, the PhD student who led the study, explained that their research emerged from a workshop at Caltech's Keck Institute of Space Studies. The workshop brought together experts in geochemistry, orbital dynamics, and mission science to discuss high-priority scientific objectives that could be achieved through sample returns from various bodies throughout the solar system. One of the most compelling reasons for pursuing these challenging missions is to understand what materials existed in the inner solar system during its early formation billions of years ago. Without samples from Mercury and Venus, we lack crucial data on the carbonaceous and non-carbonaceous materials that formed these planets. The researchers made their case by building on knowledge gained from previous missions like NASA's Messenger to Mercury, and looking ahead to active missions like the European Space Agency's Bepi-Colombo, currently en route to Mercury. They also considered proposed future NASA missions to Venus, like Da Vinci and Veritas, as potential precursors to eventual sample return missions. But the challenges are immense. Mercury's proximity to the Sun makes it extraordinarily difficult to reach, while Venus has a crushing atmosphere and surface temperatures hot enough to melt lead. These conditions make landing, collecting samples, and returning them to Earth technologically daunting. Despite these obstacles, the Caltech team believes that with the development of advanced propulsion technologies, particularly nuclear thermal propulsion, a Mercury sample return mission might eventually become feasible. Venus presents even greater challenges, with its massive gravity making it particularly difficult to launch anything from its surface back to Earth. The researchers emphasize a critical gap in our understanding of our solar system. We simply don't have any physical samples from Mercury or Venus. Tony Yap, the Caltech PhD student leading the study, puts it bluntly: we do not have a single sample in the form of a meteorite from Mercury and Venus. This absence creates a significant blind spot in planetary science. The building blocks of both planets derived from the innermost solar system remain largely theoretical. Understanding these materials geochemically would provide crucial insights into the evolution of the early solar system, approximately 4.6 billion years ago. What makes these potential sample return missions particularly significant is that they might represent the missing component needed to explain Earth's composition. Currently, scientists cannot fully account for our planet's composition using known meteorite materials. There's a piece of the puzzle missing, and Mercury or Venus samples might provide it. The technical challenges, however, are formidable. For Mercury, the team believes nuclear thermal propulsion could eventually make a sample return mission feasible. This advanced propulsion technology would provide the necessary power to escape Mercury's gravity well while managing the extreme heat near the sun. Venus presents even greater obstacles. Its massive size creates a much deeper gravity well than Mercury, making it extraordinarily difficult to launch anything from its surface with enough velocity to return to Earth. The planet's crushing atmospheric pressure and extreme surface temperatures, hot enough to melt lead, further complicate any sample collection mission. Given these challenges, researchers are exploring alternative approaches for Venus. Balloon-based technologies that could float in the more temperate upper atmosphere are being considered. These floating laboratories might collect atmospheric samples or potentially even surface material without requiring a traditional landing and return mission. Moving forward, the scientists emphasize the need to develop these advanced technologies while simultaneously building stronger scientific cases for sample returns from the inner planets. As Yap notes, figuring out how to maximize scientific value from even a single gram of material scraped or drilled from these hostile planetary surfaces will be crucial to justifying such ambitious missions. Next on today's story list. A fascinating new study published in the journal Icarus challenges the prevailing notion that Earth's water came from asteroid impacts. For decades, the scientific consensus has suggested that water or its components arrived on our planet via asteroid bombardment after Earth had already formed. But now, University of Oxford researchers have uncovered compelling evidence that the building blocks for water may have been here all along. The team examined a rare type of meteorite known as an enstatite chondrite, which is particularly significant because it shares similar composition with the materials that formed early Earth approximately 4.5 billion years ago. What they discovered was surprising: hydrogen present within the meteorite's chemical structure. This finding suggests that if this meteorite material could naturally contain hydrogen, then the primordial Earth likely did too. Perhaps most convincing about this research is how carefully the scientists worked to determine that the hydrogen they found was original to the meteorite, not the result of terrestrial contamination after it landed. This distinction is crucial. If the hydrogen was merely from Earth exposure, it wouldn't tell us anything about our planet's early composition. To investigate this, the researchers employed a massive machine called a synchrotron that produces powerful X-rays to probe the meteorite's chemical structure. They initially expected any hydrogen to be linked with sulfur molecules and targeted their analysis accordingly. To their surprise, they found areas rich in hydrogen sulfide just outside where they anticipated, with the highest concentration locked within crystalline structures. The smoking gun came when they examined areas of the meteorite showing signs of earthly contamination, cracks, and rust. These sections had little to no hydrogen present, strongly suggesting the hydrogen elsewhere was native to the meteorite itself. This evidence points to a revolutionary conclusion. The proto-Earth likely already contained sufficient hydrogen to explain our planet's current water supply. By the time the young planet had grown large enough to be struck by asteroids, the essential ingredients for water were already present. As Oxford professor James Bryson, one of the study's authors, explained, "We now think that the material that built our planet was far richer in hydrogen than we thought previously. This finding supports the idea that the formation of water on Earth was a natural process, rather than a fluke of hydrated asteroids bombarding our planet after it formed." While this research may not completely resolve the debate over Earth's original water source, it significantly strengthens the case for an internal origin rather than an external delivery system. The implications extend beyond Earth, potentially helping us understand water formation throughout our solar system and beyond. The Oxford team's investigation methods were particularly ingenious in their pursuit to determine whether the hydrogen was truly original to the meteorite. To precisely pinpoint hydrogen's presence, they utilized a powerful X-ray beam from a synchrotron, essentially a massive particle accelerator that produces incredibly intense light, used to examine the atomic structure of materials. When they aimed this sophisticated equipment at the Antarctic meteorite named LR12252, they discovered something remarkable. The hydrogen wasn't distributed randomly throughout the sample, but was specifically concentrated in hydrogen sulfide locked within crystalline structures of the meteorite. This specific positioning is significant because it suggests the hydrogen was incorporated during the meteorite's formation, not afterward. What makes their evidence particularly compelling is the comparison between different areas of the same meteorite. The sections showing clear signs of terrestrial contamination, like cracks or rust formations that developed after the meteorite landed on Earth, contained virtually no hydrogen. If contamination were the source of all the hydrogen, we would expect to see higher concentrations in these damaged areas where Earth materials could more easily penetrate. Instead, the pristine, uncontaminated sections held the hydrogen, creating a strong case that this element was part of the meteorite's original composition. Tom Barrett, an Oxford graduate student who worked on the study, described their excitement at this discovery. "We were incredibly excited when the analysis told us the sample contained hydrogen sulfide, just not where we expected. This finding fundamentally shifts our understanding of Earth's water origins. Since enstatite chondrites are believed to represent the building blocks of our early planet, their hydrogen content suggests Earth naturally contained the essential ingredients for water from its very beginning. Rather than requiring a cosmic delivery service of water-rich asteroids, our planet had the necessary components all along." The implications extend beyond Earth. This research could help explain water formation throughout our solar system and may even inform our search for potentially habitable exoplanets. If water formation is a natural byproduct of planetary development rather than depending on chance asteroid impacts, the potential for water-bearing worlds might be much higher than previously estimated. Next, if you've ever felt like becoming an entrepreneur of some note, you may have picked a good time to be alive. Let me explain. Now imagine it's 1625 and you're an ambitious young entrepreneur. The world's most powerful nations have pushed wooden shipbuilding technology to unprecedented heights. The oceans are no longer the barrier to commerce they once were. New continents have been discovered, with gold to be found, spices to trade, and fortunes to be made. Of course, there were risks, violent storms, shipwrecks, and pirates lurking in wait for merchant vessels. Fast forward 400 years, and we find ourselves at a remarkably similar threshold. Instead of wooden ships, we have advanced spacecraft. Instead of crossing oceans, we're venturing beyond our atmosphere. The comparison between these two eras of exploration is not just poetic, it's profoundly accurate in terms of the opportunities and challenges we now face. Space launch technology has evolved at a breathtaking pace, particularly in the last decade. What was once the exclusive domain of powerful nation-states is now accessible to private companies and ambitious startups. Earth's atmosphere, which for millennia represented an absolute barrier to human exploration, is now regularly traversed by both crewed and uncrewed missions. The potential rewards of this new frontier dwarf even the riches sought by those early maritime explorers. We're not just talking about discovering new trading routes or finding gold. We're contemplating mining asteroids rich in precious metals, harnessing unprecedented energy sources, and potentially even finding the answers to humanity's oldest questions about our origins and whether we're alone in the universe. Space traffic is projected to grow exponentially over the next 5 to 10 years. It's not unreasonable to imagine regular trips to the moon by the end of this decade, with Mars and even the asteroid belt becoming accessible in the following years. Currently, we use space primarily for communications and Earth observation, but that's merely scratching the surface of possibilities. Just as the age of sail brought risks alongside its rewards, our venture into space comes with inherent dangers. The space environment itself is incredibly hostile to human life. Vacuum, radiation, micrometeorites. These are the modern equivalents of the storms and reefs that threatened early sailors, and as space becomes more commercialized, we'll likely face new challenges in terms of security and competition for resources. For every entrepreneur who sees opportunity in mining asteroids, there may be those who see opportunity in piracy or sabotage. Nations with early advantages in space capability will have tremendous economic and strategic benefits over those who lag behind. The dynamics of power and wealth that shaped Earth's colonial era may find new expression in our expansion beyond our planet. Yet unlike our ancestors who sailed into the unknown with limited knowledge and primitive tools, we venture forth with the accumulated wisdom and technology of our entire civilization. The possibilities before us are limited only by our imagination, our courage, and our ability to cooperate across national boundaries for the benefit of all humanity. Space traffic is expected to grow exponentially in the coming years as humans explore new worlds and seek fortune beyond Earth. While the concept of space tourism gets plenty of attention, it's merely the tip of an iceberg of commercial possibilities whose depths we have yet to fully comprehend. The initial focus of space commerce will likely center around three key areas: resource acquisition, energy production, and advanced manufacturing. These aren't just speculative ventures. They represent logical extensions of existing needs coupled with emerging technological capabilities. Asteroids present perhaps the most tantalizing near-term opportunity. Many contain vast quantities of rare earth minerals and precious metals in concentrations far exceeding those found in Earth's most productive mines. A single asteroid with the right composition could yield trillions of dollars worth of materials critical to advanced technologies and manufacturing processes. Meanwhile, the moon has drawn renewed interest not just as a stepping stone to deeper space, but as a valuable resource in its own right. Its surface contains abundant helium-3, an isotope extremely rare on Earth, but potentially ideal as fuel for future nuclear fusion reactors. If fusion power becomes commercially viable, lunar helium-3 could become one of the most valuable commodities in the solar system. The unique environment of space also creates opportunities for manufacturing processes impossible on Earth. Zero-gravity conditions allow for the creation of perfect crystals, ultra-pure pharmaceuticals, and exotic alloys that cannot be produced under terrestrial conditions. As launch costs continue to decrease, the economic case for orbital manufacturing becomes increasingly compelling. For ambitious companies looking to stake their claim in this new frontier, several market niches are emerging. Manufacturing will be crucial, not just for Earth-based customers, but for the infrastructure of space itself. Long-range transports, mining systems, and lunar bases will all need to be constructed, potentially on orbit, to avoid the limitations of Earth-to-space launch systems. Logistics presents another massive opportunity. We'll need transfer stations, refueling depots, and efficient transport networks. The companies that develop reliable, cost-effective ways to move people, equipment, and resources throughout cislunar space and beyond will be the equivalent of the shipping companies that dominated oceanic trade. Of course, all this activity will generate unprecedented demand for information management, communication systems, navigation networks, and security services. The data infrastructure needed to support operations across the solar system will dwarf our current internet in both complexity and capacity. The countries and companies that master these challenges will enjoy economic advantages comparable to those gained by maritime powers during the age of exploration. But unlike Earth's resources, the resources of space are virtually limitless, offering the potential for growth and prosperity without the zero-sum competition that has characterized much of human history. Next, time to check in with the JWST. The James Webb Space Telescope has recently turned its powerful infrared eyes toward NGC 1514, a fascinating planetary nebula sitting about 1,500 light-years away from Earth. This celestial object has a particularly intriguing history in the annals of astronomy. When William Herschel first discovered it in 1790, the nebula's unique appearance forced him to reconsider fundamental assumptions about the nature of nebulae. Prior to this discovery, Herschel had believed that all nebulae were simply masses of stars too distant to be resolved individually. But NGC 1514 presented something different, what he described as a lone star surrounded with a faintly luminous atmosphere. This observation marked a significant shift in astronomical understanding, suggesting that not all nebulous objects were comprised of stars. Fast forward to modern times, and this curious nebula continues to yield new insights with each technological advance. NASA's Wide Field Infrared Survey Explorer, WISE, previously detected a pair of rings around the nebula that are only visible in infrared wavelengths. Now, the JWST's unparalleled capabilities have allowed astronomers to examine these structures in unprecedented detail. Led by Michael Ressler, a researcher and project scientist for Webb's mid-infrared instrument at NASA's Jet Propulsion Laboratory, the new observations reveal the complex and turbulent nature of NGC 1514. The JWST's mid-infrared imager and medium-resolution spectrometer have clearly resolved the nebula's distinctive rings, showing them to be relatively distinct structures with both filamentary and clumpy details throughout. What makes these new observations particularly valuable is how they've enabled astronomers to peer through the nebula's history, tracing its evolution over approximately 4,000 years. As Ressler noted, before Webb, we weren't able to detect most of this material, let alone observe it so clearly. The telescope's infrared sensitivity has provided a comprehensive view of the nebula's turbulent nature, allowing scientists to examine features that were previously impossible to detect. The detail revealed by these observations offers a time capsule of sorts, recording the dramatic processes of stellar evolution as they've unfolded over millennia. By studying the intricate structures within NGC 1514, astronomers can better understand the complex interactions that occur when stars reach the end of their main sequence lives and begin shedding their outer layers into space. A pair of binary stars reside at the center of NGC 1514, appearing as a single purple star with bright diffraction spikes in JWST images. This central system is actually what powers and shapes the entire nebula. One of these stars was originally several times more massive than our Sun, and, as it evolved into a red giant, it cast off its outer layers of gas, which form the distinctive nebular structure we see today. David Jones, a senior scientist at the Institute of Astrophysics on the Canary Islands, who proved there is a binary star system at the center in 2017, explains this process. As it evolved, it puffed up, throwing off layers of gas and dust in a very slow, dense stellar wind. That once massive star has now collapsed to become a white dwarf, while its companion is currently a giant star on what astronomers call the horizontal branch. What appears from our viewing angle to look like a can being poured out is actually an hourglass shape. There are hints of a pinched waist near the top left and bottom right of the nebula, and at these locations, the dust appears orange and drifts into shallow V shapes. This unusual configuration likely results from the interaction between the binary stars. When this star was at its peak of losing material, the companion could have gotten very, very close, Jones notes. That interaction can lead to shapes that you wouldn't expect. Instead of producing a sphere, this interaction might have formed these rings. The JWST observations have allowed researchers to dig more deeply into the nebula's composition, revealing something quite unexpected. Unlike many other planetary nebulae, the brightness of NGC 1514's rings doesn't come from line emissions from elements like atomic hydrogen, polycyclic aromatic hydrocarbons, or shocked molecular hydrogen. Instead, the brightness primarily comes from thermal emission from dust grains, with researchers calculating that only about 1.5% of the ring flux comes from line emissions. This composition is particularly unusual since carbon and polycyclic aromatic hydrocarbons are common features in planetary nebulae. The lack of emissions from molecular hydrogen indicates that the ring structures weren't formed by material shocked from collisions with the interstellar medium. While the new observations provide unprecedented clarity about what the rings are made of, they haven't yet fully explained how they formed. Researchers suggest that a strong thermal pulse from the binary star's common envelope may have created pronounced changes in density in the surrounding material. Alternatively, a period of heavy mass loss followed by fast jets or winds could have carved out material along the poles to create the ring-like structure. As the researchers concluded, the new data do complete the picture of the rings being cool, dusty structures embedded in the tenuous outer shell of a very complex but fascinating planetary nebula. Finally today, shifting our gaze from distant nebulae to events much closer to home, sky gazers have an exciting opportunity coming up with not one but two meteor showers visible in our night skies beginning in late April. These celestial light shows offer everyone a chance to witness the beauty of space without the need for expensive equipment. The Lyrids meteor shower will be the first to grace our skies, active from April 17th to 26th. These meteors are actually tiny pieces of debris from the Thatcher comet that interact with Earth's atmosphere and disintegrate, creating those beautiful streaks of light we associate with shooting stars. The Lyrids take their name from the constellation Lyra, which contains the bright star Vega. This is the region of the sky from which the meteors appear to radiate. What makes the Lyrids particularly special is their long observational history. People have been spotting these meteors for at least 2,700 years, making them one of the oldest recorded meteor showers. While they may not produce the highest rates compared to other major showers, they often compensate with numerous bright meteors. This year, the peak activity occurs on the night of April 21st, with the best viewing just before dawn on April 22nd. Hot on the heels of the Lyrids comes the Eta Aquarids meteor shower. These meteors have a more famous parent. They're the icy and rocky debris originally shed by the renowned Halley's Comet. When these particles eventually reach Earth's atmosphere, they create their own fiery nighttime display. The Eta Aquarids can be seen between April 20th and May 28th, with optimal viewing between midnight and dawn on May 5th. The Eta Aquarids are named after one of the brightest stars in the constellation Aquarius, Eta Aquarii, which is near the point from which the meteors appear to originate. Astronomers note that the Eta Aquarids are particularly interesting because they sometimes produce strong outbursts in certain years, though this year is expected to show more moderate activity. There's an interesting hemispheric divide when it comes to viewing these showers. The Lyrids are best observed from the northern hemisphere, while the southern hemisphere provides superior viewing conditions for the Eta Aquarids. That said, both can be seen from either hemisphere, just with varying degrees of visibility. While the Lyrids might produce around 10 to 20 meteors per hour during their peak, the Eta Aquarids can display about 30 meteors per hour from the southern hemisphere and between 10 to 30 from the northern hemisphere. The Eta Aquarids sometimes leave glowing dust trains in their wake that remain visible for several seconds or even minutes, adding an extra dimension to the spectacle. If you're hoping to catch either of these meteor showers, location and timing are everything. For the Lyrids, northern hemisphere viewers have the advantage. Head out in the dark hours just before dawn, particularly on April 22nd, and look up. You won't need any special equipment, just your naked eyes and a bit of patience. The meteors will appear as fast streaks of light across the sky, and occasionally you might spot an especially bright flash. During peak activity, you could be rewarded with anywhere from 10 to 20 meteors per hour. For those in the southern hemisphere, while you won't have the best view of the Lyrids since the constellation Lyra stays below the horizon for most southern viewers, you'll have the prime seats for the Eta Aquarids in early May. This shower favors southern hemisphere observers, who can expect to see around 30 meteors per hour during peak activity. Northern hemisphere skywatchers needn't feel left out, though. You can still catch about 10 to 30 meteors hourly, but you'll need to look toward the horizon as the radiant point remains lower in your sky. One challenge for northern viewers of the Eta Aquarids is the limited viewing window. The shower's radiant only rises a couple of hours before dawn, and daylight arrives before it climbs high in the sky. This gives you just a brief opportunity to spot these meteors, making proper preparation even more important. For optimal viewing of either meteor shower, astronomy experts recommend finding a location with minimal light pollution, far away from city lights if possible. Bring along a star map to help locate the relevant constellations, though the meteors themselves can appear anywhere in the sky. A reclining lawn chair or camping mattress will make the experience much more comfortable, as you'll be looking up for extended periods. Dress warmly, even if the spring night doesn't seem that cold initially. When you're sitting still for long periods, temperatures can feel much chillier than expected. Remember that your eyes need about 20 to 30 minutes to fully adapt to the darkness, so avoid looking at your phone or other bright lights once you've settled in. Keep in mind that patience is key. Not every meteor you see will necessarily be from these specific showers, but the ultimate experience of watching the night sky come alive with streaks of light is well worth the wait. And that's all for today's episode of Astronomy Daily. From sample return missions to our solar system's most challenging planets, to the surprising origins of Earth's water, the new frontier of space commerce, the JWST's stunning observations of NGC 1514, and the upcoming meteor light shows in our night skies, the universe continues to amaze and inspire us. I'm Anna, and it's been my pleasure to bring you these cosmic stories today. If your curiosity about our universe has been piqued, there's always more to discover at our website, astronomydaily.io. There you can catch up on all the latest space and astronomy news and listen to our complete library of past episodes. We're also active across social media, making it easy to stay connected with our cosmic community. Just search for Astro Daily Pod on Facebook, X, YouTube, YouTube Music, Tumblr, Instagram, and TikTok. Remember that whether you're scanning the night sky for meteors or contemplating the origins of Earth's water, we're all explorers of this vast and wondrous cosmos. The universe is full of mysteries waiting to be unraveled, and we'll continue bringing them to you right here. Thanks for joining me today on this journey through space. I'm Anna, and until next time, keep looking up and wondering about the magnificent universe we call home.